In the previous video, I said the test error is the most important thing. Okay, then how to optimize the test error? Unfortunately, it is impossible to know the test error when you train your model, because test error means literally the error for testing, and you don't know which test point will given to you, because this is test, right? So in chapter 5, we will learn how to estimate the test error using cross validation. Okay, so in this video, I will not explain how to optimize the test error, but I will explain very important concept, the overfitting and bias variance trade-off. After you understanding all the variance bias trade-off and overfitting term, you can understand how to control your model to improve your test accuracy. Okay. So before moving to the overfitting or bias variance, I want to first classify your statistical machine learning into two parts. One is parametric learning and another one is non-parametric learning. Okay. I'll give you a very simple example. Let's say again there are one variable input and one variable output, and there are 4 data points. So again, the horizontal line is input x and vertical line is output y. So now you have to find the f hat that is close to real function f, but we don't know what is f. So to find f hat, there are two possible approaches. First, you assume that f hat x is equal to beta 0 plus beta 1 x shape. So with this form, we then optimize some objective function defined with the 4 training data point called mean squared error, like this. So here we can control beta 0 and beta 1. And the beta 0 and beta 1, they are parameters. Essentially, we optimize this MSE loss function. So we want to minimize MSE loss function, and essentially MSE loss function is function of beta 0 and beta 1, and we can control beta 0 and beta 1. So the learning process is the process finding beta 0 and beta 1 that minimize the MSE loss function. So this is called parameter learning, and maybe the result is this. Non-parametric learning, there is no parameter. One popular example is k nearest neighbor. KNN is the one popular idea for non-parametric learning. For instance, k equal to 1, we only consider the most nearest neighbor. For instance, in this case, let's say for this point, for this input, the most nearest neighbor among the 4 training data point is this, right? The x1, the distance to x1 is the least one among 4 distance. So the output just follow the output of the most nearest neighbor. So the result will be this. For this learning process, we never use any fixed form of function. We just find the nearest neighbor among all data points and then follow the output of the nearest neighbor. That's it. So this is called nearest neighbor algorithm. And another side remark for this approach is when k equal to 1, the training error is always 0 because we follow the nearest neighbor, and at the training data point, the nearest neighbor is itself, so the point just follow the corresponding output y. So there is no mistake at all for training data point. Right. Okay. So let's focus on parametric learning first. Imagine there is ground truth function f, and because of the observation error, we have a bunch of data points like this. To fit the training data point, we can consider this parametric learning model. And we can control beta 0 and beta 1 so that the MSE is minimized. But we can also consider another type of model, second order polynomial. Like this. We can consider third order polynomial, and so on. Okay. Then which polynomial is the best? This is not easy question indeed. And this is the very important question when you design a machine learning process. Alright, let's consider the case f hat 1, the first order polynomial. Then maybe the result is this. This is reasonably good, but there is some limitation. The linear line cannot capture the curvature. The linear line cannot learn these smooth curves. Okay, so this is the limitation of very simple model. And this kind of error, the error due to the simple model, is called bias error. I will tell you why this error is called bias. Okay. On the other hand, if you increase the number of parameters, so you increase the order of polynomial. So let's imagine you use hundreds or millions of order of polynomial, then maybe the result looks like this. Because you have a lot of degree of freedom, your model can follow all the training data point and you can make the training error almost zero, right? So do you think this is good line to predict your new data point? No, not at all. So these two wiggly curves are unnecessary details there, right? And which can make a very bad test error. And this is true because the ground truth function f have this shape, right? So there is some gap. So for new data point, you can expect some error, right? So when you draw this kind of figure, so x-axis present the number of parameters or complexity, and then usually the training error always decrease because you have more degree of freedom. You can follow the training data point more easily. But in terms of test error, at the beginning the test error also decrease, but at some magical point it increases. Usually the test error has some U shape, and this gap is called generalization error, or overfitting. This is very important concept for machine learning. We have to design an algorithm so that we can escape from overfitting.